Thank you, Danuta, for a very kind introduction. Actually, it also is good for introduction of my talk and motivation of the study that I want to present to you. For me, it is a great pleasure that actually I can speak in such a great group of scientists. So I would like to thank Danuta and the Stellar for giving me this opportunity to this talk. And my talk, as it was already said, will be about the ionogels, or in particular about the thermoreversible ionic gels and the interactions at the liquid-solid interface studied by field cycling NMR. So the outline of my talk looks as follows. First, a few words about the motivation, why we started this study, and actually why it is important branch of industry right now, also in the research field. I will introduce the object of our study and the specific properties of the materials that we used to create the ionic gels. And then a few words about the methods. Of course, the field cycling will be the leading one, but to give you the wider picture of the systems that we study, I need to mention about a few more methods. And then I will come to the results, which I would like to show you and discuss the interpretation and the data that we get. So the motivation, or one of the motivations that stay behind this project, was actually the car branch. If we focus on the engines and the future of the engines. If we look at the numbers, in 2020 year, there will be around 2 billion cars in the world. And I'm meaning the cars which are using combustion engines. So mainly what they generate, of course, is a pollution. And nowadays we are very aware of the natural habitat and want to protect it on any kind. So one of the future tasks for the scientists and engineers is, of course, to reduce the pollution from the transport and the vehicles that we are using. So one way to do it is to actually switch to a different kind of engines, the electric ones, which do not create pollution during using it. But if we stop at this point, of course, the future is coming because more and more electric cars are present on our streets. But to be responsible for our environment, we have to think in advance what danger can bring this solution. Of course, electric engines does not create pollution. However, the power source, mainly the batteries which we are using in them, can constitute a problem when it comes to disposal of used or damaged batteries. If we look again on the numbers, in 2019, there were only like 3.3 million electric cars on the world, and this number counts for hybrids, plug-in hybrids, and any other kind of vehicles that use electric power. So this is a very small number compared to normal, let's say, traditional cars. It is less than 0.2%. But I'm sure that in the next years, maybe 10 or 15 years, this number will grow significantly. And if we don't solve a possible problem connected with the batteries, then we end up with another kind of situation where not the pollution, but dump yards full of used batteries will be a danger for our environment. So the solution which we have already on market is batteries which use gel electrolytes. So this is a progress. We do not use anymore, or tend not to use batteries with liquid electrolytes, but electrolytes in the form of polymer gels. And this was a big progress and step forward, as the safety issue is now much better. These systems are more safe and also easier to operate. They can also work at different conditions and at different positions. So for example, on boats, this is a very desired solution. However, polymers which are used to create the gel polymer electrolytes has also some drawbacks. One is, of course, that it reduces the mobility of the charge carriers and also limit the conductivity that can be achieved by these systems. But during using these materials, in the internal structure of the polymer electrolytes, some defects occurs, and they are occurring naturally because of the exploitation. So mainly these are some cavities or discontinuities in the matrix, which degrades and limits the conductive properties and finally makes the battery useless. What we can do with this, actually not much, because we have to dispose such battery, put it on the junkyard. And because these systems are based on polymers, then of course there is an issue with the recycling. It is quite difficult and consumes a lot of energy. Moreover, some of the polymers have very long degradation periods, and if we don't solve this problem, then we will end up with another danger for the natural habitat when the electric cars will take over the traditional cars. So what we can actually do, and what is observed in the research, is that we look for another type of system which also will be able to create or produce solid electrolytes, but will be easier to handle and less dangerous for the environment. And one way of doing this is using or creating organic ionic gels. These systems are very similar in composition to gelled polymer electrolytes. However, the gelling agent is of a different type. Here we use the low molecular weight organic gelators. Mainly these are small organic molecules of natural origin, which have the ability to gel different solvents. And this accounts for water, polar solvents, organic solvents, and different types of other liquids. The main difference between polymer system is that these molecules use physical interactions to create a gel state. This can be hydrogen bonding, van der Waals interactions, pp stacking, and so on. And the physical nature of these interactions give the advantage over polymer ones because these interactions are reversible. By changing the temperature of the system, we can go from liquid to the gel state and vice versa. And this gives us the possibility not only to recycle those systems, but also preserve their lifetime. Because when we arrived at the point where the battery is used and lots of defects is in the internal structure, we do not have any more to dispose this battery, but just heat it up to dissolve the matrix, go to liquid state, remove all discontinuities, and gel it again by lowering the temperature. In the end, we have like a new system with nominal parameters, which allows it to use it again. Also, the recycling process is much easier and less energy consuming. Unfortunately, this has also some drawbacks, but when I will talk, before I get to this, just a picture of what kind of molecules I'm talking about. So on the top, you can see an example of low molecular weight gelator. This is a derivative of glucopyranose, and actually, this is nothing else like a monosaccharide. So you can see that it's a very neutral to the environment molecule. It can create gels with a variety of different liquids. Moreover, we can put different type of ions into it. It can be different type of salts, but also ionic liquids. So another type of materials which is very popular nowadays. Sorry. And what are the advantages with the, let's say, ionogels based on low molecular weight gelators? They have a solid-like phase. They are highly conductive. As I will show you later, the conductivity is on the level of liquid electrolyte. They are thermally reversible, eco-friendly, and they are very easy in manufacturing. In case of polymer systems, a lot of effort needs to be put in order to get good quality electrolyte, polymer electrolyte and contact with electrodes. In case of ionogels, this is not so crucial issue, as when it happens that the connection between the electrolyte and the electrodes is bad, we can just heat it up and then cool down to repair this situation. The drawbacks or the weak side of the system is that because of the physical nature of the forces that create the gel phase, the mechanical strength of such system is rather moderate, and the temperature range which the gel phase exists is also medium. However, a recent research in developing new low molecular weight gelators already given examples where the temperature range is over 120 degrees, which is already good for applications. Okay, to show you how easy actually is to create such kind of ionogels, I will show you a short movie. And this is not the exact example of my Ionogel system, but it shows you how the process looks like. It is very similar. So of course we start with the electrolyte solution, which can be of different, which can contain different types of ions or other charge carriers. Then we use some low molecular weight gelators. In this case, can be xanthan gum. And what we do actually is dissolve this gelator in the liquid electrolyte solution. This phase of the process usually involves high temperatures around the boiling point of the solvent, just to dissolve and melt all the molecules of the gelator. But when everything is solved, then it is enough to actually cool down this mixture containing gelator and the ions to transform the liquid sol phase into gel phase, what you can observe here. At the end, we result with a material which is very similar to what we observe on this picture. And you can see this very easy. It doesn't have to be expensive equipment used to do it. So this may also lower the cost of production. Now, a few words about the methods I would like to speak about. Of course, the field cycling will be the key one. However, I need to also talk other NMR methods, which delivers evidence for unexpected phenomena which we actually found in the system. And just to turn on your curiosity, I will also mention about the thermal scanning conductometry method, which was developed in our group to characterize the system, especially during the gel-sol-gel phase transition. So very briefly, because we already have heard about the field cycling and we are all experts in that field, this is a basic picture which shows the idea behind the method. So the key information here is that field cycling allows us to run NMR experiments in function of magnetic field strength at which the a relaxation process takes place, in contrast to a standard NMR spectroscopy where we use superconducting magnets at one fixed magnetic field. Depending on the magnetic field strength, we use different pulse sequence just to increase the sensitivity and the signal-to-noise ratio of our system. In terms of pulse field gradient diffusometry NMR experiments, it is an experiment which allows us to trace the translational motion of the species that we are interested in. For most of the cations, as we are talking about ionogels, there are protons in it, so it is very easy to follow with NMR. And in most of the anions, we found other NMR active nuclei, which also can be registered. So in principle, with this pulse field gradient diffusometry, we are able to trace the movement of the spin system of the particle which are interested and observe the attenuation of the signal caused by the translational motion. And then one more method, which actually the basics for it are known since, I believe, 1960s, but because of different technical problems, only in recent years, this method become available commercially. This is electrophoretic NMR, ENMR, something which is quite unique as the phase cycling, because it gives us the possibility to investigate actually how the external electric field influence on the investigated systems. So imagine that you put electric field into a superconducting magnet and investigate the system using NMR. What we get for this method, the important thing is that we get the information about the electrophoretic mobility of ions, and based on that we can calculate the effective electric charge of ions and cations in studied systems. Okay, so now just to know your curiosity. Thermal scanning contactometry, it's a modification of a conductometry which allows us to continuously record the conductivity of our sample during gelation process and in the recovery process when the internal structure of the gel phase is destroyed. So we can also find from this method what happens when the system goes from the solid-like gel phase to liquid gel phase. By changing the temperature range, scanning rates, we can do this process or very quickly or slowly, and by this we can actually control the internal structure of our ionogels. And this is an example of the data we get from the thermal scanning conductometry. So on the left-hand side figure, you can see how the conductivity of an electrolyte solution consisting of water and tetramethyl ammonium bromide salt dissolved into water looks like. The solid symbols, the triangles, are for a liquid electrolyte, and the open circles are for the Ionogel. So this is actually the reason why we were so interested in this project. You can see that this is something against our intuition. In the gel phase, when we go from liquid, so very mobile system, to a solid-like system, where the bulk flow is stopped and the motion is more restricted, we actually observe that the conductivity of such system is higher than in the liquid phase. So this is something what we were not expecting to find. And you can also notice some anomaly on that feature at high temperatures, which actually was recorded by the thermal scanning conductometry. And now just going in the future, I will tell you that it is connected with the phase transition when the system, when the internal structure of the gel network starts to dissolve. When we take a look on the right side of the slide and the upper feature, there are black squares, and these are the data obtained from a standard conductometry. And you can see that they have perfect agreement with the thermal scanning conductometry, except the anomaly. And this is only because the standard conductometry actually is not sensitive to record the phase transition when the system turns from solid to liquid. This is very well seen when we analyze the derivative of the conductivity. You can see that the standard conductometry actually has the same behavior except the anomaly. So everything is fine from the physical point of view, only the method is not sensitive for this structural phase transition. This method allows not only to see when the system starts to flow, as we call it, but it is also possible actually to determine the phase transition temperature, which is very important for application. Okay, but enough about this. So the inspiration was to find the origin of this enhanced conductivity and try to understand it. To try to explain it, let us see first how the internal structure of the Ionogel looks like. Here I present a picture taken by the polarizing microscope of the hydrogel, so a system without ions, which we use as a reference one and also the simplest case. When we look closer, we can find here aggregates which are built up from the gelator molecules, and they are marked here like this straight lines. And when we think about the solvent, how it behaves or where it is, then we can find that actually it exists at two sites. So the solvent, first, it's in the free spaces between the gelator aggregates in the pores, and then the solvent behaves as a bulk phase. And there is also a solvent molecules close to the surface of the gel network and interacts with it. Because, as you maybe remember, the molecular structure of the gelator, it is a polar molecule which creates a polar surface. On top of it, there are hydroxyl groups, which very easily interacts with other solvents, for example, water. So the first guess was that maybe something changed in the diffusion of such molecules of the solvent when it goes to gel. Because diffusion is directly related to the conductivity, because it describes how the charge carriers moves. When the diffusion will be faster, then the conductivity will be also higher. So with use of pulse field gradient methods, NMR, we measure the diffusion in the electrolyte, in the liquid electrolytes, and in the gel phase. And here I present you the example of how the spectra and the signal attenuation looks like in this experiment. It was an electrolyte composed of glycerol and tetraethylammonium bromide salt dissolved in it. On the left side, you can see the attenuation of the signals for the cations, for the glycerol, and also for residual water, because glycerol is hydrophilic. So by fitting with a mathematical formula, we actually can obtain a coefficient, which is called self-diffusion coefficient, telling us about, giving us the information how the translational motion of the molecules in the system looks like. And on the right-hand side, you can see how the diffusion coefficients change in a function of the concentration of the salt. So for low concentration, actually, there is no dependence on the diffusion coefficient. This is because the ions are very well dissolved and they are far from each other. So basically, they don't interact with it, and also introduce no change in the composition or in the density, the viscosity of the electrolyte solution. However, when we go to much higher concentrations, we start to observe that the diffusion coefficient gets smaller. And this is also something what we can understand as the electrolyte solution becomes more dense and more viscous. So the question was, because at some point especially for the high concentration, we observe B exponential behavior. So the question was, if we have two distinct diffusion coefficients or a distribution of diffusion coefficients. And to check this, we analyze the data in so-called Statistical-Tanner presentation, which you see on the left side. And we've noticed that for high concentrations of the ions, we observe two slopes. And in this presentation, such behavior stands for two different diffusion coefficients. If there would be a distribution of diffusion coefficients, then we would observe a curvature in that presentation. Okay, so that's the one point. The second point is that when you look at the dashed lines, which stands for the data obtained in the gel phase, we see that the diffusion coefficient, although the system turns from liquid to solid-like, is very similar to what was observed in the liquid state, although still a bit smaller. So, in principle, increased diffusivity of the ions or other liquid molecules cannot support the increased conductivity. So this was something what we expect. First, that we don't get the answer in that easy way, but also decreasing the diffusivity of the molecules when we go to more restrict motions is something what we would expect. However, because of the specific experiment, and also because the amount of the gelator is very less, on the level of 2 weight%, with this pulse-field gradient method, we are not able actually to see what happens at the surface of the gel matrix. So to be sensitive to these interactions and to the part of the system which actually takes place at the surface of the gel matrix, we turn to field cycling NMR. And on this slide, I present you two nuclear magnetic resonance dispersion profiles. And the black one is for our reference system, which is the hydrogel system. And the red one is for the Ionogel. You can see actually that the shape of the Nmrd profiles in the gel phase is similar, and also the relaxation rate is similar. So to interpret and analyze this data, let's first start from the hydrogel system, which is less complicated system. Before I go to the interpretation, just a quick look how the Nmrd profiles looks for ionogels with higher electrolyte concentration. So you can see that we went from 500 millimolar concentration of the salt to almost 3 molar concentration of the salt. So it's a very big difference. And just because on the qualitative, let's say, aspect of the record Nmrd profiles, we can divide them into two groups. For a low concentration of the salt, up to, let's say, 1 mole, we observe a very similar Nmrd shape and also similar relaxation rate, which is around 0.7. And for the high concentration of the ions, we see that the Nmrd profile shape is changing. This is mainly due to also a shift of the Nmrd profile for a pure electrolyte solution, but the value of the relaxation rate, especially at the lowest field, stays on the same level. Okay, so again, like a summary of those data, we can see two things. If we look at the electrolyte solutions, we see that when we increase the concentration of the ions in the electrolyte solution, the relaxation rate becomes faster. And I will comment that on that in a moment. And when we look at the right figure, which are the Nmrd profiles for the Ionogel with different ions concentration, we see that for low concentrations, the profile is very similar even to the hydrogel where there is non-ionic system. And for high concentrations, except for the high frequency part of the Nmrd profile, the low frequency part of the Nmrd profile is also very similar and ends at the same or almost the same relaxation rate. Okay, so to explain first why the relaxation rate change when we add more and more ions. This actually can be related or can be explained by in two possible ways. First, the viscosity of the system change. When we increase the number of ions in the liquid, in the water, then the density of the system also increases. And because of the mutual interactions, also the viscosity of the electrolyte increases. When those parameters increases, the molecular dynamics, the motions are slowing down. So the dipole-dipole interactions are stronger and thus the relaxation rate is faster or the T1 relaxation time is getting longer. But if this would be the explanation for this effect, when we analyze the derivative of the R1, the relaxation rate, then we would observe the shift of the inflection point, which is the point where the curve changes its slope. So what we see on the right figure actually shows that the inflection point stays for all systems at the same place, starting from non-ionic distilled water and ending on the very high concentration of the ions in the electrolyte solution. Moreover, the value of the magnetic field, the frequency, which is 10 megahertz, is also very characteristic one. So this data does not support that the increased relaxation is due to change of the viscosity. The second possible explanation is the interaction with a paramagnetic species. In case of distilled water, it is known that there is, especially we did not degas the samples, so there is a portion of molecular oxygen dissolved in the water. And this molecular oxygen is, of course, paramagnetic. So we observe interaction between nuclear spins and electron spins. And of course, when we prepare our electrolytes, what we do actually is we add more and more ions, and in the case of tetramethyl ammonium bromide, the bromine anion is also paramagnetic. So the increasing relaxation rate in the electrolyte solutions comes from the interaction between nuclear spin and electron spin. Okay. And now, let us take a closer look to the Nmrd profile of the Ionogel. Not for the Ionogel, but for the hydrogel first. We can see a very strong dependence in the only 2% gel phase at the room temperature. So the open triangles are in the gel phase, the solid triangles are for the pure water. Because the Nmrd profile for the pure liquid is almost like a constant in whole frequency range, and we are especially interested in the low frequency range, we did a small trick, mathematical trick, just to make the situation simpler for analysis. We actually subtract from the Nmrd profile of the gel the Nmrd profile of the liquid. In that way, somehow we ruled out the influence or the contribution from the liquid which stays in the pores of the gel matrix and behaves as a bulk solvent. And we are more sensitive now to the contribution coming from the solvent molecules at the surface of the gel matrix interacting with the gelator molecules or very close to the surface matrix. And here on the right, you can see this profile. So this is the effect of the subtraction. And later in this presentation, I will show you this type of Nmrd profiles. Okay, we know that field cycling NMR relaxometry allows us to study nuclear relaxation processes in a function of a magnetic field strength. And by this, we are actually able to analyze the shape of the spectral density function, which itself contains the information about the molecular motions that actually take place in studied systems. So it is also known that if in the system there are any disturbances of the molecular motions, of the molecular dynamics, either because of some geometrical restrictions or by interactions at the interfaces, for example, at the surface of the gel matrix, it will be reflected in the relaxation behavior. And when talking about analysis of these Nmrd profiles, we need to think about the relaxation mechanisms and the molecular dynamics. And the main, or one of the mains of the spin lattice relaxation time are intermolecular and intramolecular spin-spin interactions modulated in time, for example, by translational displacement over the distances greater than the size of the molecules that we study, or by reorientation of the spin system that we investigate. And the former one results from the fluctuations of the interproton distance between the molecules, separate molecules. And the later one comes from the fluctuations of the orientation of the spin-spin axis in the molecule, resulting from the rotational diffusion. And under the assumption that both types of molecular dynamics are stochastically uncorrelated, those intermolecular and intermolecular dipole-dipole interactions then contribute additively to experimentally observe T1 relaxation time. So let's think what is possible mechanism of this Nmrd, which can be used, which model can be used to analyze this Nmrd profile. And of course, we can start from the simplest one, like magnetic cross relaxation, and then using appropriate conclusions and statements, we can go to more complicated ones. So magnetic cross relaxation is a model which assumes or which we can use when one of the two main requirements is fulfilled. So the first one, either we have a direct dipole-dipole interactions between the protons of the diffusing molecule and the protons coming from the internal structure of the gel matrix. But we know that because in case of the ionogels, the ions are surrounded by solvation shell created from the solvent molecules, and also the surface of the gel matrix is covered by water or other liquid molecules. So there is a very low probability that the ions will directly interact with the surface of the gelator aggregates. The second reason is that there is a chemical exchange of unstable protons between the protons from the gel matrix and the protons from the diffusing molecule or ions. And this is also not the case as the ions does not have exchangeable, the cations does not have the exchangeable protons. So we ruled out this process. The second one, the two fraction fast exchange model, actually assumes the existence of at least two dynamically inequivalent spin reservoirs, which are interacting with each other. And moreover, they are in a fast exchange regime. Fast in terms of the T1 relaxation time. And if we take a closer look on the internal structure of our ionogels, even if we restrict to hydrogels, then we see that we can find solvent molecules, water or others, at least at three different states. So first, there will be a solvent molecules in the volumes of the pores, which behaves like a bulk solvent. Then we have the solvent molecules around the ions, creating the solvation shell. And those molecules will mimic, let's say, the behavior of the ions. And then we have the solvent molecules at the surface of the gel matrix. So at least three states. Even in this simplest scenario, with use of the two fraction fast exchange model, it would lead us to over-parameterization of the model. So of course, we are able to get a good mathematical fit to experimental data, but we are able to get equally good fits for different sets of parameters. And because of this, the data or the results are unfortunately not very reliable. So we also exclude this approach. So now we turn ourselves to reorientation mediated by translational displacement, Nmrd model, which I believe is familiar to you. It is a model which assumes that we have strong adsorptions at the surface of the, in our case, gel matrix. And the absorbent molecules are the solvent or the ions that can stack to the surface of the gel matrix. Of course, this is possible when we have a strong polar system in terms of the surface of the gel matrix and in terms of course of the diffusing molecules. And from our previous studies, we know that the molecules of the low molecular weight gelators, they are polar itself, but they also create a polar surface. And also the water or the glycerol or even the ions which have the electric charge are also very polar, and surely they can be adsorbed at the surface. So in this approach, we see the strong liquid surface interaction. And what it actually makes. When we imagine let's say, single molecule of the diffusing solvent, which is adsorbed at the surface of the gelator matrix, we can, because of the strong adsorption, its orientation is somehow predefined by the surface at which it is adsorbed. And because the surface is not regular, it's not flat, but is very irregular, when in time the molecule travels on the surface, the predefined orientation of the spins in the molecules is changing in time when it's moved from a point to another point on the matrix. And this makes the fluctuation of the orientation or reorient the spin system by translational displacement on the surface of the gel matrix. And because of this, the RMTD process is an effective relaxation mechanism of liquids confined in porous media, especially well seen at low frequencies. So to describe this effective relaxation rate, we can, in the case of our reference system, we can assume two contributions. One, which can be described with the spectral density function of Lorentzian form, and it will be for the solvent molecules which does not directly interact with the surface of the gel matrix. And the second contribution will be described by the RMTD model, is for the molecules that interact dielectrically with the surface of the gel matrix. So the low frequency range dispersion will be described by RMTD, and the high frequency range dispersion will be described by the BPP with a Lorentzian form of the spectral density function. If we go more into the details to the RMTD model, which I will not do at this moment, we arrive at some important parameters. And among them, there are two which can deliver us information about how the translational motion looks on the surface of the gel matrix. And this is so-called surface diffusion coefficient, and also the Lmax parameter, which describes the maximum distance at which the molecule is traveling on the surface. So now we focus on the low frequency range of the Nmrd profile. Okay, so maybe we can ask ourselves questions, what we are counting for, or what we were counting for, in the sense of finding explanation for the enhanced ionic conductivity effect. Well, my colleagues in other types of a system and other other project, actually were investigating a polymer electrolyte with what's based on some imidazolium ionic liquid. And actually what they found was that molecules of this ionic liquid at the surface of the gel matrix, of the polymer gel matrix, have bigger diffusion coefficient than in the bulk. And this was explained very well and also supported by other methods, that in this case, it was because changing the three-dimensional diffusion process to a two-dimensional diffusion process. So we were thinking that maybe this is also the case in our system. So this is what actually occurs when we did all the analysis. And we got this surface diffusion coefficient for the molecules diffusing on the surface of the gel matrix in our system. And actually, what we found was here that the surface diffusion constant was about 10 to minus 14 square meters per second. And if you maybe remember, the standard diffusion coefficient for bulk water at room temperature is around 2 times 10 to minus 9 square meters per second. So what we actually see here, what the field cycling told us, is that the liquid molecules in the hydrogel, the water molecules, at the interface and the surface of the gel matrix diffuse much slower than in the bulk. Okay, so but still we have hope, as hope dies the last one, that maybe in the ion gel the situation is a bit different. So we use the RMTD model to analyze the Nmrd profiles for the ionogels. And this is an example of 500 millimolar ionogel. So we add another contribution just to describe the molecules which actually create the solvation shell around the ions. So we have a contribution for the solvation shell. We have the contribution for the molecules which are close to the surface of the gel matrix but does not interact directly with the surface. And we have a contribution with the molecules which directly interact with the surface of the gel matrix. This is how the fit looks like. The black solid line is the overall fit consisting from these three components. So the red dashed line shows the results from the RMTD model. So it describes the molecules at the surface of the gel matrix. And what are the parameters? Well, it was something what we could expect, but we actually count that it may be different. That is the surface diffusion, the coefficient of the solvent at the surface of the gel matrix is like 10 to minus 12 square meters per second. And if we now go back to Pacific gradient diffusion experiment and we look for the diffusion coefficient of the either solvent molecules or the ions, the cations in this case, in the gel phase, so the dashed lines here, we see that the diffusion coefficient is on the like 10 to minus 9 square meters per second. So field cycling shows us that in case of our ionogels, the diffusion at the surface of the gel matrix is also much slower than in case of the bulk solvents. Okay, so how to explain the increased conductivity effect? Well, to have a better picture, we also ran the analysis for a higher concentration of ionogels. And we observe here also that although the diffusion coefficient is higher, but I will explain in a moment why, its value is still below the value for the liquid electrolyte. And in case of the highest concentration, because also of the low resolution which we get from the normal field cycling experiment, and because of the very big fraction of the ions and the water molecules in the solvation shell, we are no longer able to distinguish them from the molecules at the surface. Therefore, we have to change the RMTD model for a log Gaussian distribution type of spectral density function. But how to explain the increasing surface diffusion coefficient with increasing of the concentration of the ions? Well, this is because of the internal structure of the sample. It was quite specific and important for other reasons that when we created those systems, we always kept constant the concentration of the gelator to the fraction of water. So it was always like a 2% gel, LMWG molecules to water fraction. But when we increase the concentration of the electrolyte, then we increase the number of salt molecules and decrease the number of water molecules in the same volume. And this caused that actually the internal structure of the gel network changed substantially from very well developed here, a rod-like structure. In this case, we were observing the enhanced ionic conductivity effect. And in this case, we observed that the surface diffusion of the liquid molecules was much, much smaller than from the bulk ones. In somewhere in the crossover region, when the matrix of the gel is dissolved, it starts to dissolve. So we do not observe the bulk flow, but the internal structure starts to change and basically dissolve the well-defined aggregates. We observed the increasing of the surface diffusion coefficient. And actually for the highest, it was already very close to this diffusion coefficient observed for a bulk or pure electrolyte. This is because the fraction of the gel matrix was actually too small to support the gel state. And we have, like almost everywhere, free diffusing molecules of the solvent. Okay, so we now understand why and how the surface diffusion changed in our system, but we still do not know how to explain the enhanced conductivity effect. And at that point, we were a bit stressed because we were really hoping that field cycling give us the answer. Well, it only shows that in science, in the research, you actually cannot expect that if some solution works for one system, it can also work for other. In that case, the enhanced diffusion at the surface observed for ionic liquid and polymer gel is not working in case of ionogels. So then we start to think what actually diffuse in the system and what this slow surface diffusion coefficient applies to. And it occurs that it applies to the molecules of the solvent, water or other solvent, but not to the ions itself. So we have a situation where in contrast to the liquid state, a part of the solvent molecules somehow is, I would even say, hindered, because 5 orders of magnitude slower diffusion, we can say that it is almost like static molecules at the surface compared to those in the bulk, diffusing very fast. So a part of the solvent molecules which can, for example, collide with the ions and slow them down, is like hindered by the gel matrix. So the ions basically have more space or less obstacles on the way. So the conductivity can be more efficient. So this could support the increased conductivity effect. But the question is it the only explanation? So I have the opportunity actually to go abroad to Sweden, to Professor Furo group, where I got possibility to work with electrophoretic nuclear magnetic resonance. And this is a fantastic technique because it allows us to investigate how the electric field actually influence on the system that is studied by NMR. And in case of ionic systems, the influence of the electric field plays a key role. So because I don't have the time to explain the method itself, it could be a topic for a separate lecture. I only want to say that with this method, we can get direct evidence and information about two key parameters. This is the electrophoretic mobility and the effective charge of diffusing ions. And this applies for cations, which mostly have a protons in its structure, so it's very easy to measure with NMR, and ions, which have other nuclei active species that can be measured. So this is an example of the Ionogel composed of the system that I show you the data for field cycling NMR. So you can see a big line of the water, okay, we are not interested in that now, but the small one comes from the cation, and we observe that in function of electric field, sorry, this should be here electric field indicated. So we are increasing the electric field from 0 to in this case it was 500 volts per centimeter. And we observe the phase shift of the signal from the cation. So analyzing this, not going into details, we could calculate the effective charge of the cation. And actually what occurred was actually that in the gel phase, the effective electric charge of the tetramethyl ammonium cation was higher than in case of the pure electrolyte, which is the solid dots here. And the gel is the open circles. So this gives us very important information. What is the reason for the higher electric charge is still an open question, but definitely it can increase the conductivity, the overall conductivity of the whole system. And this could also support the information from the field cycling that because of the presence of the gel matrix, which entraps some part of the solvent molecules, the solvation shell can be thinner because less molecules of the solvent is available to do this. And because of that, the screening of the electric charge of the ions is less. So the effective charge is higher. And what is more important, we observe the same effect for the anion. So both cations and ions in the same Ionogel has higher effective electric charge. Okay, so going to conclusions. I would like to say that the Ionogels are interesting materials worth to be studied as they allows us to create systems which are highly conductive, which display enhanced conductivity effect that can be actually used to monitor the internal structure of the gel itself. These materials are thermoreversible, so we can use it and prolong its lifetime if it is necessary. because of the water or solvent molecules adsorbed at the surface of the gel matrix, this matrix becomes invisible to ions and they can move more freely. And I believe, or I hope, that I have showed you that field cycling NMR is a very important method which delivers key information in those systems, which allows us to get the information what happens at the liquid-solid interface in case of those ionogels, but also for other systems. And as a final conclusion, I would like to show you this simple information, why the ionogels, or what is the advantage of the organic ionic gels over the gel polymer electrolytes. So when we use the standard batteries with polymer electrolytes, after, let's say, 1,000 or more recharge cycles, the systems becomes degraded, and what we can do is only dispose them. In case of organic ionic gels, of course, this process is faster because the driving forces and the physical interactions which creates the gel phase are more fragile. So the system is used faster, but it is easy to recover its primary properties just by appropriate thermal treating. So in the end, we result with a new battery, but in the old package. So we can use again and again the same battery. And at the end, of course, I want to thank all the people, colleagues and friends from my laboratory and other groups which we collaborate with for having its support in this project, from the Sweden group for the possibility to run the NMR experiment, but also from a PL Scientific company which builds and sells the NMR equipment just to let us testing to the limits of the apparatus with our samples. And of course, colleagues from our institute which support those investigations. Also, a part of these measurements were supported by National Science Center of Poland as a scientific project. And thank you very much for your kind attention, and hope that we can discuss later.